Okay, so as we continue on in our chapter, we're going to be looking next at sample problem 4.1, where we have a crane. It's a fixed crane. It's telling us that the mass of it is 1,000 kilograms. This means that we are in the metric system. They always give in units of mass. That's a kilogram. So we're going to have to convert it to newtons, which we'll see in just a bit. It's used to lift a 24 kilogram crate. Again, we're going to have to convert it to newtons. It is held in place by a pin at A and a rocker or kind of like a roller at B. The center of gravity of the crane is located at G, and they're giving us the dimensions for that. Okay. Determine the components of the reactions at A and B. I like to say, find the reactions at the supports. Our supports are at A and B. They all already told us that A is a pin and B is a roller or a rocker. So first things first, we have to draw a free body diagram. So we're going to do that on page 5 here in our guided notes. I'm going to do a straight line across at A. Okay. And we're just going to move those forces along their line of actions horizontally. And then I'm just going to go down here a little bit, and my B is going to be down here. Okay. Even though the crane itself is up at an angle, we're moving the forces vertically so that we can kind of deal with them more in a, I don't know, a regular way. So this is going to be point A, and this is going to be point B. I know that at G, I have the weight of the crane. So I'm going to call that WT, and we'll calculate that in just a bit. And then out here at the very end, and I'm going to call that C. It's not a point right now, but I'm going to call that C. This is G. And this is going to be the weight of the block. We'll call it WB. I should probably call this WC. I don't know if I want to call it that. Now I have C there. I'm going to keep it WT. Weight of the crane and then weight of the block. So, and then I'm going to add my distances. This is 2 meters. This is 4 meters. Oops, don't forget your convention. I don't want to miss that. And then my distance A to B vertically is 1.5 meters. Okay. Now, external forces wise, we have those on there, but let's calculate for our weight. So I'm going to do that over here. So the weight of the crane is going to be equal to mass times gravity. Okay. They gave us the mass of the crane is 1,000 kilograms. And we're going to multiply that by gravity, which is 9.81 meters per second squared. A kilogram meter per second squared is a Newton. So the weight should come out to be 9,810 newtons. Is that right? Okay. So this is going to be equal to 9,810 newtons. They convert to kilonewtons, but we're fine. I'm going to do it in newtons. It's no big deal. Then WB then, it's going to be the same thing. It's going to be mass times gravity. The mass here was 2,400 kilograms. And we're going to multiply that also by 9.81 meters per second squared. So our WB, I got to do it on my calculator. It's going to be 23,544. And that's going to be newtons. Equals 23,544 newtons. Okay. So those are the values that we're going to go with. If you wanted to do kilonewtons and divide each of those by 1,000, that's fine. But I'm gonna do it in newtons. It's no big deal. Now those are our applied loads, the ones that are there. Now we need to determine what are the reactions at the supports. Our two supports are A and B. Let's look at A first. A, as identified in the problem, they said A is a pin connection. So if we go back to page 160, that would be a frictionless pin. So it is going to have an X and a Y at A. So two reactions at A, X and Y. Oops. Oh, I don't have my thing plugged in. Hold on. I'll put AX and AY here first, then I got to plug my computer in. Now, I don't know which way AX and AY are going to go. I'm going to assume a direction. So this is going to be AY and this is going to be AX. I don't know if that's going to be correct or not. And I'm going to put it going towards the points here at AX. All right, let me plug in my computer quick. Did that. All right. Now, it's not a big deal. I just want to emphasize that as we had, alluded to earlier, when I get my final answer, that will confirm my direction. So all I'm going to do right now is I'm just going to assume a direction. I don't know if it's right or not. If it looks like it's obvious, then I'll put it on in a direction. But right now I'm like, I don't know which way that's going to go. So I'm just assuming an AX and an AY. And then once we do our math, as long as I end up with a positive value for my final answer, I can say yay. If I don't, then I'm going to show you how we can change it. Same thing at B. We're going to assume a direction. B was a rocker, which is in the same category as a roller. So it's going to have one reaction perpendicular to the surface it's riding on. As we look at the orientation of B here, it's riding on a vertical wall. So it's going to be perpendicular to that wall. So we're going to show it going to the right. Okay. And this is going to be BX. Okay. So that is our free body diagram. We have our distances. We have each one of our vectors identified, and then all of our vectors have arrowheads. Okay. Now we are ready. As we look here, we actually have 3 unknowns. All right. But we're going to be using, the 3 equations of equilibrium. We should be able to get it done here. So, as we look, our step number 1 is our diagram, free body diagram, and our convention. Step number 2 is going to be those equations of, kind of abbreviated here, equations of equilibrium. Okay. Now, in this case, we do have some x-directed forces, right? So we probably are going to have an opportunity here to use the sum of the forces in the x. So let's go ahead and start there. Let's say sum the forces in the x direction equal to 0. Remember, you always have to tell me what you're going to do and then go down and do it. So as we look in the x direction, we have AX going positive plus BX going positive. Those are the only 2 forces in the x direction. Set them equal to 0, right? That's as far as we can go. That's no problem. We can always come back. The next one we're going to do is sum the forces in the y equals 0, okay? So looking in the y direction, I have an AY negative because I assumed it going down. I have a negative 9,810 newtons. And then I have a negative 23,544 newtons. And that's all my forces in the y. So I set it equal to 0. This is good news. I only have one unknown here, right? So I can combine what I have and solve for AY. So go ahead and do that. You get a negative AY is equal to 33,354 newtons. Yeah. Now, this is one of the cases where we have a negative in our final answer. What that means is, notice it's negative and our force is going down. It doesn't mean, oh, the force is going down, it has to be negative. It means that by putting it negative in a negative direction, I assumed the wrong direction because this is a final answer. So it's a 2-part process to fix this. I need to, number 1, make a positive in front of my AY. You never hand in a negative final answer, okay? Never. If you have a negative final answer, you're not done. And then what you're going to do is you're going to go up here because you did this in pencil, okay? And you're going to switch the direction of AY. So I look, what are the directions of your forces in your diagram? So you have to fix it in both places. You don't have to recalculate. You would notice that this would then become a positive here and you would work out. Just make your final answer positive and then change the direction up here opposite of whatever you assumed. Make sense? Okay. So make sure that your final diagram always has the correct orientation of the forces. Okay, so we can put a box around our AY because we're not leaving it negative. Okay, and I have one more equation of equilibrium, okay? I'm going to sum my moments. Now I have to sum my moments around one of the points where my unknown forces are. They're at A and at B. So where do we want to sum around? Do we want to sum around A or do we want to sum around B? Let's just do A. All right, let's do A. Let's go back to the norm. So I'm gonna leave a little room underneath my X because I know I'm gonna add here. So I am going to sum my moments around point A equal to 0. So I'm gonna go up here. That means I take out AY and AX, which is good. So I'm gonna start with BX since it's right here. That is going to rotate in a counterclockwise direction. So it's gonna be positive out front. So BX times perpendicular distance from A is going to be 1.5 meters. Okay. Then I'm going to put my finger on A again. I'm going to rotate in the direction of the weight. That's 9,810 newtons times perpendicular distance, 2 meters, and it is rotating clockwise. So it's going to be negative out front. So 9,810 newtons times 2 meters, negative out front. And then go back up and I've got my 23,544. That's also going to go in a clockwise direction, multiplied by 6 meters. And that is going to be negative out front as well. Those are all of my moments. Set it equal to 0. Now I only have the one unknown BX, so go ahead and solve, and I'll do it on the side here as well. Okay, I know it's in the rounding. Did you get 100,552? No? You did, okay. Okay, done, divide right. I must have not divided by 1.5 correctly. I must have keyed in something different. I get it now, 107,256 Newton meters. There we go, yep. So BX, this is my value. Notice that my BX came out to be a positive value, Brooke.
Would it just be newtons?
Oh, you are correct. Oh, see, I was testing you. Thank you. I canceled out my moments. Yes, or I'm sorry, my meters. And yes, it is just in newtons. Thank you, Brooke. And I think Danny, was that your voice? There we go.
Yeah, sorry.
Okay, awesome. So now that we know what BX is, we can plug it back up here into our sum of the forces in the X. So we can say AX plus 107,256 newtons is equal to 0. We're going to move that to the other side. AX is going to be equal to a negative 107,256 newtons. What does that mean to us? Can we leave it? No. It says we did not assume the correct direction for AX, okay? So as a final answer, we're gonna make this positive because we never leave final answers as negative. And then we're gonna erase our arrowhead going to the right for AX, and we are going to reassign it going to the left. So again, your final drawing needs to reflect the correct directions. So, you know, that's where I like to let students know, don't get too hung up when you are trying to put in the direction of the supports. Just put them in. If you know that it's a pin reaction, just put an X and a Y and like just assign it, because we found in two cases, two cases here, our AX and our AY, we found that they were negative values, which just meant, oh, no big deal. We assumed the wrong direction. We just put it in the opposite direction and we can move on. All right. It confirms it as a final answer. So all final answers need to be positive values. Okay. Do not hand in anything with a negative value. All right. All right. How did we do on sample problem 4-1? Any questions? Kind of fun, isn't it? I know you guys are looking forward. Like, let's get into the homework already, right? Ah, I don't blame you. Should we do one? Should we do a homework problem? The heck?
Yeah.
Yeah, let's do one. So if we look at our application problems, let's go back over here. What I'm going to do is I'm going to stop the recording here, and then we'll do one of the application problems as its own video. So that probably makes sense.